Good morning. I'm Frank Walsh, Operations Manager for New Projects at EM Corporation. Over the past several months, I've taken this factory from an idea on paper to a fully operational facility. This presentation summarizes the key decisions and analyses that got us here. Here's our roadmap. We took a systematic approach, starting with picking the right location, then designing the plant, forecasting demand, setting up inventory systems, scheduling operations, planning workforce, and finally, implementing quality controls. Each step built on the previous one. And let me walk you through each. We evaluated 3 candidate locations using a weighted factor rating model, which scores each site based on labor availability, shipping proximity, construction costs, community acceptance, and proximity to headquarters. Location C came out on top with a score of 410 versus 307 for location A and 245 for location B. Financially, location C also had the highest annual net at $1.42 million. The main trade-off is a larger initial investment and moderate distance to the headquarters. But we mitigated that with our stronger on-site leadership and remote collaboration plans. This analysis used concepts from Chapter 8 of the Stevenson textbook on location planning. For the plant layout, I used a systematic layout planning approach from Chapter 6 in the Stevenson textbook. First, I sized each workstation based on daily volume, process times, and efficiency rates. We need 5 molding stations, 14 internal assembly stations, 12 external assembly stations, and a few inspection stations. Then I built a Muther relationship chart to define which departments must be close together and which must be apart. The key constraints: molding must be far away from the office and assembly areas for safety, while inspection needs to be right next to shipping. The final layout achieves a total load distance of about 2,138 load feet per day. You can see on the right the actual proposed block layout. Each cell is 5 by 5 feet, color-coded by zone. Notice how molding is in the top right, isolated from the assembly areas in the center. And shipping is at the bottom with direct access, well, close to direct access to the bay door access. Forecasting was critical to get right before we started production. I tested multiple methods from Chapter 3, naive, simple, and exponential smoothing, and looked at seasonal patterns. For the widgetator, simple exponential smoothing, or SES, with an alpha of 0.30 gave us the best results with about 11% of error. For Wideroo, the demand had a recent step change that broke the seasonal models, so the naive method actually performed best at 7.7% error. I also audited both plant forecasting methods and found Pawnee is more accurate but consistently under forecasts, while Eagleton is less precise but unbiased. Understanding these biases helps us set a better safety stock. Once we knew what we'd be building and where, we needed to figure out how much raw material to order and when. Using economic order quantity, or EOQ for short, the model from Chapter 13, I calculated optimal order quantities for all 14 Wideroo components. The tricky part was converting between production units and supplier units. For example, we need 225 grams of pellets per Wideroo, but we buy pellets by the 680 kilogram bin. Sound chips are our biggest single cost driver at about $17,500 per year. The total annual material cost comes to roughly $84,000 per year, and we've set up ordering frequencies that balance holding costs against our order costs. When it comes to scheduling, we had 11 trucks, 1 dock door, and about 450 usable minutes in the day. I tested 2 priority rules from Chapter 16, earliest due date, or EDD for short, and slack per operation, or SO for short. EDD was slightly better on average at 73.9 minutes of tardiness, but it pushed the Sullivan truck past his 2 p.m. hard deadline. The SO rule here averages 74.9 minutes of tardiness and meets every constraint, and those constraints being that Bardstown goes first for the perishable goods. The other cool constraint that we added was that the brakes stayed fixed. We didn't move them to game the numbers, so workers get their nice spaced out brakes. Workforce planning was one of the most nuanced analyses. Demand swings from about 6,400 units in June to over 11,300 in March and November. I built 4 aggregate plans from Chapter 11. Plan 1 hires and fires each month to match demand exactly. Expensive, at nearly $7 million, and bad for morale. Plan 2 keeps a constant workforce of 99 people and allows a small backlog in November, the cheapest at $6.67 million per year and the simplest to execute. Plan 3 uses 100 workers with 0 back orders but has almost no slack. Plan 4. Once production started, quality was the next focus. I collected defect data from the WIDEX inspection check sheets for a full week. 237 total defect observations. Using a Pareto chart from Chapter 9, material thickness was the clear leader at 42% of all defects. The top 3 categories cover 83% of the total defects. For the improvement approach, I recommended starting with a focused Six Sigma project on thickness because it forces tight problem definition and measurable before and after results. At the same time, we borrowed Total Quality Management's best feature, making fixes into standard work so the gains stick after the project team moves on. Uses 99. The final piece of the quality puzzle was setting up statistical process control from Chapter 11. I analyzed 50 samples of 10 thickness measurements from each from our first inspection station. Using standard control chart constants, A2, D3, D4 for n equals 10, I constructed both an X-bar chart to monitor the process mean and an R chart to monitor variability. The good news is that every single point falls within control limits on both charts. This means that the variation we see is random, common cause variation. The process is stable and in control. No adjustments are needed. This gives us a solid baseline for ongoing monitoring. To wrap up, we went from an empty site selection spreadsheet to a fully operational, quality-controlled factory. Every decision along the way was backed by data and proper operations management methodology. Location C gives us the best combination of costs and logistics. Our layout minimizes material handling. Forecasting models are tuned to each product. Inventory is optimized with the EOQ. Scheduling meets all constraints. Workforce planning balances cost with stability. And our quality systems, Pareto analysis and statistical process control, keeps us producing consistent, high-quality products. I'm proud of what we built, and I believe that this factory is well-positioned for long-term success. Thank you for your attention in this matter.